Okay, now we're going to work on work problems. That's their name, work problems. Ones where there's a constant force and ones where there's a variable force, and we're just lightly going to touch on this. But I assigned you to do reading, I think it was 450 through 457. Most of that reading is, there are example problems. Read through each of the examples. We're only going to practice a certain type for this course, but read those examples so that you have a broader knowledge. Okay, so we're going to pretend for a moment that Shoshana, very bad drawing of Shoshana, sorry about that, Shoshana, is going to push this 225 pounds 20 feet. The reason why we're pretending, well, first of all, I doubt she's pushing a fridge anywhere, but the idea that Shoshana would know that she's pushing something at a constant rate, not likely. She'd probably push it really, really hard at first and then get tired and kind of lighten it up. But we're going to pretend, we're going to suspend reality. We're going to pretend that she can keep the constant push rate, the force, right? So it's a simple, straightforward work is equal to the force times the distance. Well, here's our distance, and the force is in terms of the weight of something and its unit. So work is equal to 225 pounds times that 20 feet. And when you simplify it, the notation is spelled out foot-pounds. It is not this. You actually write out the word foot-pounds. All right, so that's constant force. Variable force is a little bit different. So variable force is when obviously it's not constantly pushing or pulling at the same rate, because work can be pulling something or pushing something. Again, look at those examples in the book. And this is the setup for finding variable force problem. So here's our situation. We have a cylinder full of oil at 62.4 pounds per cubic feet. That's the given. How much work to push the oil to the top? So sometimes you're going to have an object and you're going to be pushing horizontally. Well, that would be dx. If you're pushing vertically, then that's going to be a dy. Remember, the y-axis is vertical, the x-axis is horizontal. All right, so here is kind of also a lame drawing of the situation. Now, there's two ways to approach this. Sometimes you're going to go that full height. You're going to start down here, go all the way to the top, and the B to A is from 0 to 10. But maybe you're only going part of the way, so maybe you'd only go 5 feet or whatever that distance is, and then it would be the height subtract the y value. So I'll show you in a sec. So here is the capital F is equal to that 62. Remember, we have this disc right here. We have this disc of oil that we're pushing up, and the area for this disc is pi r squared, right? And the depth of that disc is going to be represented by the dy. And from A to B is simply the y value right here. The y from 0 to 10 feet, that's the y value. And so, given that information, we're going to go from the bottom to the top, so 0 to 10 feet. We're going to do the force. Now, I'm going to leave off the labels for right this minute. When you write out the labels and you put in the y, which is ends up being the 10 feet, that feet and the feet squared end up canceling with that feet cubed. That's how those things cancel, leaving the pounds. So 42.4 times pi, the radius is 2 feet, so 2 squared times y dy. So let me come over here. So this is what we have. I have it written out. I'm going to simplify this. 2 squared is 4. And then 4 times the 62.4 is 2496, or 249.6 pi y dy. So that's what I have right here. And notice when I multiplied this, these things are now a constant. And the 249.6, I went ahead and pulled out of the integral. And now we're just integrating the y. So work is equal to the 249.6 pi. The integral of y is y squared over 2 from 0 to 10. And then it's f of b subtract f of a. I really need to pay more attention to what I'm doing. So when you plug the 10 in and the 0 in to the f of b and the f of a, you end up getting 12,480 pi foot-pounds is your answer. Now, you could end up, the other setup would be, let's say you're only pushing a distance of 4 feet. So it'd be from 0 to 4. And then you would have your 62.4 pi, the r squared. And then instead of y, it's going to be 10 subtract y dy. And then you just have to simplify this, then do the distributive, and then go ahead and integrate. All right, those are the work problems. Given that information, you should be able to do the handful of problems that I assigned in the book. All right, that's it for now.